You can switch now the camera off if you want.对啊，我有30点。这是在家离开，对吧？你是在家离开，今年你今年是离开，对吧？最好是如果看到他们手跟他们坐着嘛，OK， 好。Okay, so it's about time. Let's start with the class today. My TA will be not here today, so I hope there is no technical problem. So in case you don't hear me for the online parts, just let me know. I want to remind you that next week we will have our midterm exam. It will be from, I announced it already last time, so it will be from 9:10 to 11. There will be no class afterwards, so it will be then. It will be only 2 hours next week on Wednesday. So what else? I already announced what is covered by the midterm exam. There are some students who will do the midterm exam online. I maybe say this once more because some students who are doing also the quiz online, the camera is not adjusted in the right way. It's not you who should be in the camera. It should be your hands and your table mainly. Okay, so please, for some of you doing the quiz every week online, please adjust the camera such that the table and your hands are visible. The same is true then for the students who will do the midterm exam online next week. And for the students who do the exam online, you will be responsible for the camera, for the internet connection. So you make sure that your internet connection is going to work. So are there any questions for the midterm? Any questions? So if not, then we are going to. I'm told that I don't need the mask anymore. That's the that's not true for you. That's only true for me, because there is enough distance anyway. Already since many months. So I wanna today continue with section 4.3. So last time what I discussed was what we focused at was what can we learn about the function by looking at the derivative. What does the derivative tell us about the original function? Now today I want to discuss the question, that's the first thing I want to discuss today. What does the second derivative tell us about the function? Now if you look at the function, so we saw for the first derivative, if for instance the first derivative is positive on the interval, then the function is increasing on the interval. Now there are two different types of increasing. One increasing is like this, and one increasing is like this. These are essentially two different types of increasing function. Now, what is the difference between those two types? If gives us the slope of the tangent. So here, if you plot tangents, you will see that the slope of the tangent is increasing, is an increasing function. That's one observation you can make. Another observation which you also can make is that the tangent is always below the function. Here the tangent is always above the function, and you see the slope of the tangent. As I go from here to here, it's getting smaller and smaller. Okay, so here the slope is increasing, here the slope is decreasing. And another observation, which is actually the same observation, is that here the tangent is always below the function. A function where the tangent is always below the function is called concave upward. So this function is called concave upward. So this function where the tangent is always below the function, above the function is called concave downward. So, some authors also use concave and convex, but we are sticking to these two notations: concave upward and concave downward. Now. So since you see here that the slope is increasing, so this means that the second derivative must be positive, because the slope of the is given by the derivative. So if the slope is increasing, this means the derivative is increasing, which means the second derivative must be positive. And here, the second derivative must be negative. This is the explanation if you look at the slope. This doesn't explain why. So we have the following theorem. Concavity test. I formulate it as a theorem. Consider the second derivative is larger than 0 on an interval I, then f is concave upward. On I, and if the second derivative is smaller than 0 on I, then f is concave on I. So that's sometimes also called the concave. How to prove this? I think the proof is not in the textbook, but it's in the maybe in the appendix, because some of the proofs of the results in the textbook you find in the appendix at the very end of the textbook. But the proof is not hard, because it uses again the mean value theorem. So for instance, if you want to prove one, okay, so pick a point in the interval I, and another point x in I with, let's say, for simplicity, let's say x larger than a. If x is smaller than a, then the argument is similar. Now, since the second derivative is larger than 0, so this means the first derivative is increasing. So you will have the first derivative at x is larger than the derivative at a, right? Just the increasing property for the derivative, because this means that the first derivative is increasing. And now you look at the function. Y is equal to. Then you look at another function which I call g of x, which is the tangent at the point A. So that's the tangent to f at the point A. And then you use those two functions to define a function which I call h. So h is just the difference between those two functions, f of x minus g of x. Then what you see now is of h, derivative of f, derivative of g. But the derivative of g is very easy to compute because it's a linear function, so it's just the derivative of f at a. Now we said this is larger than 0. So this means what? This means this function h is increasing, right? So this means from here we know that h of x is increasing. Which in turn means that h of x must be larger than h of a. But if you compute h of a, then you see this is just 0. So this means that f of x is larger than g of x. So indeed, the This is the tangent, this is the function. The function lies above the tangent. This is this proof only works for this range here. If you have x is smaller than a, then you have some modifications to do, but it's more or less the same argument. What you get here is smaller. Right? It's increasing. You just do the same. You compute this here, then you get here smaller. So now this function is not increasing, it's decreasing. Right? So here you get the inequality in the other direction. And here also. Here the equality is the same. Because as you move away you're getting larger again. So you just get the same conclusion. As you move away from decreasing, if you move to the right, so that's the proof of the first item. And second item is just the same proof. Or you can say for the second item, if you have a function satisfying this property, you replace f by minus f. Then you can use the first property. Then you get that minus f is concave upward, but this means that f is concave downward. So this means that if the second derivative is positive, the function is concave upward. If the second derivative is negative, the function is concave downward. So the points are of interest where the behavior changes from concave upward to concave downward, or the other way around. These are the points where the second derivative is equal to 0, or the second derivative doesn't exist. These are the points where the function might change the concavity behavior. And the points where the function changes the concavity behavior are called inflection points. So I'm going to erase this. So that's a definition. So x is f be a function which is continuous at x is equal to a. Then a is called the inflection point. If f changes the concavity behavior at x is equal to a. So this means either going from concave upward to concave downward, or from concave downward to concave upward. And if the function has a derivative at a, I'm not necessarily requiring that the function is differentiable at a for this definition. If the function has a tangent at a, then if a is an inflection point, then the function must cross the tangent at a. Because that's clear, because if the function changes from concave upward to concave downward, concave upward means the tangent is below the function. Concave downward means the function is the tangent is above the function. So if you have a tangent at the inflection point, then suddenly the function must cross, the graph must cross the tangent. Not that I require here continuity. You could say this not continuity, but if you have a function which jumps, for instance, at A, so let's say the function is concave downward, then it jumps at A. So this point is excluded, and then it jumps, and then it's concave. It's up to you whether you. It's kind of up to your definition whether you want to call this an inflection point. It's here the concavity behavior. Well, okay, but according to the textbook, it's an inflection point. Okay, we require that the function is continuous at the inflection point. Not necessarily differentiable. So if you want to find all the inflection points, you have to look at the points where the second derivative is equal to 0, but also at the points where the second derivative doesn't exist. All those points are the possible candidates of inflection points. That's a little bit like the critical numbers, which are the candidates for local extrema. Okay, so you have here something similar. Okay, so let's look at an example. So assume you have a function which has f of x is larger than 0 on the open interval from minus infinity to 1, and the derivative is not the second derivative. The derivative is smaller than 0 from 1 to infinity. That's the first property. The second property the function should satisfy is that the second derivative is larger than 0. This is true on the interval from minus infinity to minus 2, and also on the interval from 2 to infinity. And the second derivative is smaller than 0 on the interval from minus 2 to 2. Moreover, assume f of x as x is equal to minus 2, and the derivative of f of x as x tends to infinity is equal. So that's an example from the textbook. So how does a function like this look like? This first item tells you something about where the function is increasing, where it's decreasing. The second thing, the behavior, and the third are the asymptotes, the horizontal asymptotes. So let's first plot the asymptotes. So 0 is an asymptote, the x-axis is an asymptote, and this line is an asymptote. Now until 1, the function is first increasing, then decreasing. So 1 is a maximum. Actually, it's a local maximum, but it's also absolute maximum. Then from -2 to 2, the function is concave downward, and for the remaining range, the function is concave upward. So it's not hard to plot such a function. So it has an inflection point that it has 2 inflection points, one at -2 and the other one at 1. So you have the function until this point, and then it changes to concave downward. So there is an inflection point at 2, and then it goes up like this, and then it goes. Not plotted very. I'm sorry. The peak should be at 1. Okay, should be roughly like this. Here there should be an inflection point here. This should be an inflection point, and this should also be inflection point. And 1 should be the absolute maximum. That's an example for such a function f of x. So you see, if a function is increasing for all points to the left of 1 and decreasing for all points to the right of 1, according to the first derivative test for Extrema, which we saw last week, you will have a local maximum at 1, but since this property here holds for all points to the left of 1, and this property holds for all points to the right of 1, in fact what you have is absolute extrema. Now for local extrema there is another test, the second derivative test. So the second derivative test. For last time we saw the first derivative test. So here you assume that the second derivative is continuous close to z, including z. Then what you have is, if the first derivative at z is equal to 0, and if the second derivative at z is larger than 0, then c is a local minimum. Similar, if the first derivative at c is equal to 0 and the second derivative at c is smaller than 0, then c is a local maximum. If the second derivative is also equal to 0, then it's it's not clear whether you have a local max. If you compare this test with the first derivative test from last time, this test requires much more. For the first derivative test, I only require that the function is continuous at c. Here I require that not only the function is continuous at c, even the second derivative must be continuous at c, including c, close to c. For the first derivative test, you only need existence of the first derivative to the left and right of c, and continuity at c. That's much less than this. So why do I need that the function is continuous close to c? The proof actually of this is not very complicated. We just have to use far. If the second derivative is continuous close to c, this means on the interval around c. So the second derivative is continuous on an interval from c minus epsilon, c plus epsilon, for some epsilon. That's by assumption. But this means that the function will be, because if you're in the first case, so let's assume we're in the first case. If you're in the first case, then even we have larger than 0. Because the function, the second derivative at c is larger than 0. So there must be an interval. And the function is continuous at close to c. So there must be an interval around c, but the function is still 0. Which means that concave upward on I. But the function tangent because of this property. So the function is concave upward must lie above its horizontal tangent. Okay. Lies above. Yeah. At c, which of course means you have a local minimum. So this already means c is a local minimum. That's the proof of the first case. In the second case, you just replace again f by minus f, and you get the second case. If you have these assumptions satisfied, you replace f by minus f, then you can apply 0.1. Then you get that c is a local minimum of minus f. So c is a local maximum of f. Very hard to argue. Derivative test is not very important for us because we have these tests, increasing, decreasing tests, and concavity test is because we usually want to plot the function. So we have given a function, we want to understand how the graph looks like without a graphing device. Now, if you don't have access to a graphing device, you need to study certain properties of the function. Like where is the function increasing, where is it decreasing, where is it concave upward, where is it concave downward, where are the local extrema, where are the inflection points. This kind of knowledge will help you to understand how the graph should look like. Maybe what you need in addition is asymptotes, horizontal and vertical asymptotes. If you have all this information, which you can get all by differentiation. So the reason why this test is not so important, derivative. You know where the function is, where is the function increasing, where is it decreasing. So we don't have to go. is for the concavity behavior and inflection point. So let's do an example where we have then how the graph looks like. Of course, nowadays you can say I don't need this anymore because I have the graphing devices like Maple. To pick the viewing rectangle, you have to tell the graphing device to plot the function over some interval which you pick. For instance, from -2 properties you are not going to capture with your viewing rectangle. So maybe you have to try around that you find the interesting properties of the function, which are local extrema and inflection points and change and intervals where the function increases, decreases, and concavity behavior. So calculus is understand which plotting window to choose that you capture. Let's say our function is the function x to the 2/3, then 6 minus x. Let's say this is the function we are interested in. Now, the first thing you should try to figure out what is the domain of the function. So for this function, the domain is you can plug in any real number. So the domain is all real numbers. Here is no problem if this is negative because it's the third root. And here you have a square anyway, so you can even if there would be an even number here in the denominator, you can still consider this function for all x in R. First thing is we compute the first derivative. So 2/3, x to the -1/3, 6 minus x to the 1/3, and leaving this unchanged. And then minus. The minus comes from the inner derivative, because here I have to use the inner derivative. Minus 2/3. Okay, so you can write this x to the 1/3 to the 2/3. That's the common denominator. There is a 1/3. I write this, and then this is 2 times. This is 2 times 6 minus x to the 1/3 minus. No, I have 6 minus x. Okay. Minus, and here I have x. Okay, that's it. So this is equal to. If you compute this, the x you have, you can actually divide by 3. So you have 4 minus x, right, divided by x to the 1/3, x to the 2/3. Okay, so this function, this should be a 4. I'm writing it more clearly. 4. Points, which are the points where the concavity behavior changes. These are just the critical points. So you have 6 and 0. These are critical points because you see the derivative doesn't exist at x is equal to 0 and x is equal to 6 because you divide by 0. So there are 2 points, and there is 1 point where the derivative is equal to 0, which is 4. So x is equal to 0. Maybe I write it as a set. So 0, 4, and 6 critical points. Consider the intervals. X is smaller than 0. Then x between 0 and 4 and 6. X is larger than 6. Sign of if x is smaller than 0, then this will be those two are positive. This one is negative, so everything will be negative. So here the sign is negative. Sign change here. So the sign changes to positive. Then at 4, you have another sign change because of this one. So the sign changes to negative. Change because this function, this term doesn't change the sign. If you move through 6, if x is smaller than 6 and x is larger than 6, it's the same sign because of the square here. Everything is positive anyway. So it's still negative. So you see, becomes increasing until the point 4. Then the function is decreasing again and remains decreasing. So this means that you have at 0 you have a local minima. At 4 you have a local maxima, and at 6 you have neither. So x is a local minima. X is equal to 4 is a local maxima. I should already start with a big. So 0 is an important point. This is also an important point. And not here you have a local maxima. Also the function until here is decreasing. Then the function is increasing until this point and then decreasing again. You also see at 0 the function is 0 clearly. So the next thing we look at is if you consider the second derivative. You have to differentiate this. So you get x to the 2 over 3. Four over 3. Numerator, you have the derivative of this one, which is minus. So you have minus x to the 1 over 3. 6 minus x to the 2 over 3. And then x. Okay. The derivative of this one is 1 over 2 over 3. It's x to the 2 over 3. I thought it is too early. Then minus x to the 1 over 3. You have a 2 over 3 minus x to the minus 1 over 3. Now you have to simplify this a little bit. It's just straightforward computation. It's actually getting pretty simple. It's just x 3 and then 6 minus x to the 5 over 3. And then there is a minus 8 here. That's it. So this requires some simplification, but it's not very complicated. You just move everything which is negative. You can move in the denominator. This and this you also move. And then everything which remains. If everything cancels, and you get minus 8 in the numerator. So where are the inflection points? This is never equal to 0, but don't forget that the second derivative doesn't exist also at 0 and 6. Right? Because 0 and 6, even the doesn't exist there either. Okay, so the interesting point, and no point which is coming by equating this equal to 0, because this is never equal to 0. So again, you can make a table. Now the intervals you consider is smaller than 0, between 0 and 6, and larger than 6. The sign of the second derivative. Now this is always positive here because of the power 4 here. So that's always positive. This changes sign. If x is smaller than 6, then this is positive. Otherwise it's negative. So if x is smaller than 6, then this is positive. This minus here, and then plus here. And 6 is inflection point. No, 0 is not an inflection point. So 6 is an inflection point. So the function is concave, always concave downward, then it's concave upward. Okay, now we can plot it. I probably should write down the function once more. So x to the 1 over 3, 6 minus x to the 2 over 3. So the interesting points are 0, 4, and 6. 0 is a local minimum, local maximum, and 6 is a inflection point. The function is decreasing here and until 0, and the function is concave downward. This is a local minimum. The function is still concave downward until 6. 6 is also a 0, as you see. So you should have something like this. And then you have something like this. Because here the function becomes concave upward. So that's the function f of x. So you see, once you have gathered enough information about the function, it's not complicated to plot it. Of course, if the function tends to and minus infinity to understand, because this gives you just a restricted viewing rectangle. If you want to know what happens if x is very large or very small. x to infinity. Wrong. I wrote the function wrong because I was just seeing. To minus infinity, the function tends to infinity, as I plotted it here also. That's true, because as minus infinity becomes positive, as x tends to plus infinity, this is still positive. This is getting negative. So it tends to minus infinity. Okay, so this is one example of such a function, and using the results today, how to figure out the shape of the probably one more example of x, this function. For such a function, you don't need to consider the whole domain, because this is a periodic function. The sine and cosine are periodic functions. So here it's only in x to pi. Actually, even this this whole interval, you don't need to consider it, because you see that f of x plus pi is also true. So this means what? This means that the function is also symmetric about pi. Okay, so you actually just need the interval. So actually you just need to pi. Because if you understand how the function looks like on this interval, then because of this property, you get it from pi to 2 pi by just reflecting about the line x is equal to pi. And for the remaining intervals, you just get it by periodicity of the function. So that's the only interval you have to consider. So now again, so let's compute the first derivative, which is minus 2 sine of x, which 2x. So this you can write as, because sine is cosine of x. Then from here, and then minus 1. Okay, so this is the, where is it equal to 0? We are just interested on this interval. Critical points are x is equal to 0, x is equal to pi. These are and pi, and where is the cosine of x equal to 1/2? all the other points where the cosine is equal to 1/2 are outside of this interval. Okay, so we again make a table. Maybe I plot it here. So x is pi over 3. Then x between pi. And then the sign of the derivative. The sign is always non-negative. Okay. So I only have to change or not, and indeed there is a sign change because of the shape of the cosine. The sign is positive because, and here the sign is negative. This is still positive. So at x is equal to pi over 3, you have, so x is equal to pi over 3. It's a local maxima. Okay. Now for the second derivative, in order to understand the concavity behavior, it's my plus, and then here you have the cos 2x, again by the chain rule. It's now 4. Okay, so this is minus 2 cosine of x. We know the cosine of 2x is cosine squared of x, minus of x is 1 minus cosine, so let's say 2 cosine squared of x minus 1 times. Okay, so what we get is let's take out the 2. And then we have 4 times cosine squared of x minus cosine of x minus 2. So that's the second derivative. So where is it equal to 0? That's again the... You have to solve this quadratic equation. So the cosine of x is equal to 1 plus minus square root of 1 divided by. So what you get is again in this interval with alpha 1, which is the arc cosine of 1 plus square root of 33 divided by 8, and alpha 2, which is at 1 minus by 8. Yeah, there are only those two solutions because the others are not in this interval. Remember that the arc cosine, you have to the graph of the cosine. In order to define the arc cosine, you have to restrict the graph of the cosine, which I'm using here, is from 0 to pi. Okay, if you look at the cosine from 0 to pi, then the cosine
Hey, Professor. Your microphone isn't working. Yo, Professor. Your microphone is not on. Can't hear you.
That's a big problem.
It's okay now.
Now you can hear me again?
Yes, but you're really far away.
Now it's better?
The microphone is in the computer.
The microphone is from... So you cannot hear me clearly. That's the problem.
Really far away. Far away.
Better or still not better? Any improvement? Nothing yet. Because my PA today, he left. He will come back later. So maybe let's make a break of 10 minutes. I need to find someone who can help me with this. So let's make a break of 10 minutes until 10:50, and then I will go on.
就是大二这里就不一样，大概是这样。我一打电话上，他说我不会画画。我有读高中讲的，高中那我是对是读了高没有，他没有没有，他没有，我一直笑一直笑，我看过一次。可是下午4号，
几点？下午4点到5点。
不知道安迪家会不会有？
会。明天感觉很赶。明天不是还要跑事情？
对啊，我还在山上，我长在山上。
为什么你要去？
他是问那个。问他哪？他上个礼拜有上4点到5点。因为他说不来的话，可是大家会，就是按照声音走的时候，没问题。什么？
他今天有空。
他今天好满的。然后他这礼拜5中午的比较很累。
下午中午吃到这。
有点。我都想会去吧。那你在干嘛？这个礼拜我下午刚好有课，你带我回家。
没有，这几个都没有。好，所以看你，我觉得明天有点赶，所以我要跑教室。
但你知道，雷的快。我本来想说PPT 完之后，我就随便吃个，或者是我先去煮会计，只要炸。我旁边很好，居然给我买到8小炸碎，跟我一样。而且重点是，就是他不是要算的，反正这个我都不知道，我也不知道，但是我做了。要读完，我超混的。
真的超能记。
我是真的超混的。
可是我觉得比较难是后面算的那个，
反正就会录一点。
根本是会睡觉。会觉得老师教超快，因为他们就是放在那里的。
喂。喂。
Yeah, man,听得到你。What's up?
喂。
好像一开始插错洞，对，要插错到拿把去，它后面那个才是麦克风，套2个洞。
可是还没有拔的时候，他们已经说没有声音了。然后我这里有看，的确没有啊，我的麦克风。
放这个留在这边当 UP 啊。
为什么它突然会？
还是要换这个。
有可能快没电了。那如果快没电，它会关掉吗？
就是突然没声音了。你想要帮我换一电？
喂。
Now you can hear me? Okay, thanks a lot. Ah, 谢谢。Okay, so maybe let's continue. So if there is another problem with the microphone, please let me know. As I said, my TA, this is the first time that my TA will not be here. That's just because he went to get his second COVID shot. So it's that's just an exception. Usually he will be here. So okay, so now for this example, so now we have gathered all the information which we need. So we know that the function is increasing until pi over 3. Then the function is decreasing. We also know that the function has an inflection point at alpha 1 and alpha 2. If you compute the values of those two, you will see they are alpha 1 is smaller than pi over 3. Alpha 2 is larger than pi over 3. And the behavior is first concave upward, then concave downward, and then concave upward again. So the function looks like we start at 1, then the function is concave upward until there is an inflection point where it becomes concave downward. So something like, and then the function is going down, and then there is another inflection point. That's how, and here is pi. And then for the other, from pi to 2 pi, you just have to reflect it about pi. So it's now it's going up like this. Then there is the same behavior until 2 pi. And then it has a period of 2 pi. So you see, in particular, at those points, 0 and 2 pi, you have also local minima. And at pi you have a local minima. At pi you also have a local minima. That's the local maxima at pi over 3. You have the same local maxima at 2 pi minus pi over 3, which is 5 pi over 3. Just because of symmetry of the function. Okay, so you see that differentiation is quite useful because it allows you, even if you don't have a graphing device, it will eventually allow you to plot the graph of the function. But of course, usually you will need a couple of more information, not for this function. For other functions, you also will need to know what happens if x tends to infinity, if x tends to minus infinity. That's another thing you usually want to know. Also, you need probably to find intercepts with the x-axis. So zeros of this function are also of interest, just for plotting the function probably in a proper way. But if you have increasing, decreasing behavior, local extrema, concavity behavior, inflection points, that's already quite a lot. Okay, but in addition, you need to compute, of course, the function at certain points, just to see how it's located in the coordinate system. Okay, usually the zeros. So usually, like here, you want to equate this to 0 and find the solutions of it. You get those two solutions here. Then this helps you to understand how the graph is located in the coordinate system. But asymptotes are also an important important characteristics of the graph of a function. And in order to compute asymptotes, you sometimes have to compute limits which are not covered by our limit laws. So in the next section we are going to, which is section 4.4 in the textbook, we are going to discuss another way of computing limits, which are the rules of the L'Hopital. So that's the second topic I want to discuss today, rules of the L'Hopital. He's a French mathematician who was one of the first who discovered these rules. So that's about computing limits now. So now we want to go back to the problem of how to compute limits. So here is a limit which, if you have this function and you want to know what happens at 1 which should give you vertical asymptotes, then you have to compute this limit. So you would like to know what is this limit. Now, the limit laws we discussed before for computing limits, they do not apply here. Because you cannot use the quotient rule. You cannot use the limit of quotient is the quotient of the limits. because they do not apply here, because the denominator, the limit of the denominator is equal to 0. Limit of the denominator is equal to 0. You cannot use that the limit of a quotient is the quotient of the limits. If you just try to apply, you're not allowed to do this, but if you just try to apply the limit to the numerator and the denominator. I'm not writing here equality because the equality doesn't hold. Okay, so you would get something 0 divided by 0. This means you are not allowed to apply the quotient rule. You don't have equality here. Okay, so this equality doesn't hold. That's what this means. But because if you would apply it, if you get 0 over 0, we will call this an indeterminate form of type 0 over 0. So this is called the indeterminate form. Of type 0 over 0. So more generally, indeterminate form of type 0 over 0 is if you have to compute the limit x tends to a of f of x over g of x, where the limit of f of x as x tends to a is equal to limit of g of x as x tends to a. It's both equal to 0. That's indeterminate form of type 0 over 0. We are not going to give this sense. Okay, it's just terminology. That's just how we call this kind of situation if we encounter this kind of situation. Now some of the limits, even if we had an indeterminate form of type 0 over 0, sometimes we were able to evaluate the limit. So maybe it's interesting to look at an example where we are able to still, even so we encounter this kind of difficulty, we are still able to compute the limit. An example. This is not an indeterminate form. An example is this one. This is also an indeterminate form of type 0 over 0. But here we were able to compute the limit by doing what? By factorizing the denominator. So in the enumerator we have x minus 1 and in the denominator x minus 1 multiplied with x plus 1. Now if you factorize the denominator, the advantage of doing this is this guy here, x minus 1, this term is responsible for having 0 over 0. Okay. So that's because of this term we are not able to use the quotient rule. But now you can just cancel it. Okay. And now you are able to. Now you don't have an indeterminate form anymore, because now the limit of the numerator is 1, the limit of the denominator is 2, so you're not in this case. So now you can use you can just compute the limit. But how to do it for this function? The problem is you cannot, how to break ln of x into something which you can cancel and something else. Okay, that's not so obvious here, but that's actually what we want to do. Actually, by the way, we can already compute this limit, right? But in another way, not using the limit laws. Because you see, this is just the derivative of ln of x at x is equal to 1, by definition. If you write down the definition of the derivative, that's just the definition of the derivative. So we know that the derivative of ln of x is 1 over x, so this is 1. that's a little bit weird. So why are we able to compute the derivative if we are not able to compute its limit? It's a little bit strange because the derivative is defined via this limit. So why do we even know the derivative? That's because on the way I explained how to compute this derivative. On the way of explaining this, there are certain things which I haven't explained. Okay, and one of the key things is how to compute this limit. Okay, but we want to find a different way. We don't want to use derivatives. That's my point. It's just in case you object, you say, okay, I can compute a limit. It's just a derivative. Now there is another situation which is also where we also are not able to apply the limit laws. Namely, if you have the limit of, again, a quotient f of x over g of x as x tends to a, where the limit of f of x as x tends to a is equal to either plus or minus infinity, and the same is true for the limit of g of x as x tends to a. So this is also called the indeterminate form. But now of type infinity over infinity. We don't care about the sign. One of them might be negative, or both of them might be negative, but we don't care about the sign. So that's another situation where we also need to figure out a way of computing the limit. An example here. An example is you just look at the same function ln of x divided by x minus 1, but now x tends to infinity. Right? This would give you infinity over infinity. So it's also an indeterminate form. So here we also need a kind of, we need an idea how to compute this. Again, maybe it's interesting to look at an example, because sometimes we are able to compute limits even though we have an indeterminate form of this type. Namely, if you have x minus 1 divided by x plus 1. Okay. Again, this is of this type here. This is the indeterminate form. But we had a simple trick to do this. Namely, we divided the numerator and denominator by 1 over x. Then you have 1 minus 1 over x divided by 1 plus 1 over x. And then now you can use the limit law, and this is 1. Again, for this kind of function, it's not clear how to do this. Okay, the same idea doesn't work. So we need another way of handling indeterminate forms of type 0 over 0, or indeterminate forms of type infinity over infinity. And these limits are handled by what I call the rules of the L'Hopital. So the rules of the L'Hopital are a theorem, which I'm going to formulate now. So assume that f of x and g of x are functions which are differentiable close to a, not necessarily including a, and assume that the derivative of g is not equal to 0 for x close to a. Next, assume that either the limit of f of x as x tends to a equals the limit of g of x as x tends to a. And it's equal to 0, or this means you have if you look at the limit of f of x over g of x, you have an indeterminate form of type 0 over 0, or the limit of f of x as x tends to a is equal to plus minus infinity, and this means plus or minus infinity, and the limit of f of g of x as x tends to a is equal to plus minus infinity. These are still all assumptions. Then the limit as x tends to a of f of x over g of x is equal to the limit x tends to a of the derivative of f of x over the derivative of g of x. And there is one more assumption, namely provided that the last limit exists. Which also include or is infinity or minus infinity. That's also included. That means also existence. So these are called the rules of the L'Hopital. So under some assumptions, the assumptions here actually are very weak, because you certainly need that this function, the derivative of f and g exist for x close to a. Otherwise, you cannot even write this down. You also need that the derivative at x is not of g is not equal to 0 for x close to a, because otherwise this fraction doesn't make sense. These are the assumptions that you can write this down. Then those two limits are the same, provided this is an indeterminate form. This is important, and provided that this exists, that this limit exists. Also important. Existence here means also plus infinity or minus infinity, but not something more complicated. Now, why do they hold? Why is this true? In particular, what does this have to do with? I showed you the example before of a rational function where I factorized the denominator, and then I cancelled one part, and then I could use the limit laws. Why is this the same? For this, I'm. Why has the tone seem to have changed now? For this, I'm going to plot a simple picture. So assume we are in this situation. So assume this is the function f of x. and this is the function g of x, and this is my point A. So what I want to compute is the limit x tends to A of f of x over g of x. That's my goal. But if the functions are smooth enough, if the derivative of the function exists at A, here the plot might be a little bit misleading, because here I'm not going to assume, I don't need to assume that the function f and g are even defined at A. I don't need to assume this here. But here you see the functions are defined, also continuous at A, and even differentiable at A. So that's strong. They are much stronger assumptions than I need here. But for this special case, you see, if you plot the tangent here, this is the tangent to g of x at A, and the tangent to f of x at A. Okay, and as I'm getting close to A, the function should be very close to the tangent. So this means that the limit should remain the same if I replace the function by the tangent, which is here in the first case. The tangent is the derivative of f at A times x minus A plus f of A, and here it's the derivative of g at A. Times x minus A plus g of A. But f of A and g of A are equal to 0. That's because of the indeterminate form. And now you see this is the part you want to cancel, because this one is responsible for having an indeterminate form of type 0 over 0. So indeed this limit is the derivative of f at A over the derivative of g at A, and this is the limit x tends to A of derivative of f of x over the derivative of g of x. This is not a proof what I used here, because as I said, the assumption I'm using here are much stronger than the assumption I have here. I assume here that the functions are also defined at A, and that they're even differentiable at A. That's much stronger. But if you use much stronger assumptions, this actually is very easy to prove. It's not completely easy to prove if you want to prove it under these assumptions. I'm not going to show you the proof. If you are interested in the proof, you can read it in the textbook. It's in the appendix. In order to prove this, one needs an extension of the mean value theorem. This more or less follows from the mean value theorem, but one needs an extended version of the mean value theorem, which is called Cochise mean value theorem. You'll find it also in the appendix of the textbook. But the explanation should be rather should make it rather clear why this holds. So it's more or less the same trick as you saw for rational functions. You want to cancel out the part which is responsible for making the limit an indeterminate form. Now, this result actually also holds for one-sided limits. It also holds for limits at infinity. A can also be infinity. You just have to modify the assumption suitable. Okay. So let's look at some examples. So the first example is the example with which I started with. So the limit x tends to 1 of ln of x divided by x minus 1. It's very important for this result to check the assumptions. So first you have to check whether you really have an indeterminate form. This is an indeterminate form, as we checked already, of type 0 over 0. So by the theorem, this should be the same as the limit of 1 over x over 1. That's the derivative of the numerator. That's the derivative of the denominator. Actually, I'm not I cannot be 100% sure yet, because there is one additional assumption which I have to check, namely that this limit exists. Okay. Unless I know that this limit exists, I cannot write this inequality. That's this equality. That's written here, provided that the limit exists. But this limit here exists. This limit is equal to 1, so actually I can erase the question mark, and you really have equality between those two. So this limit is equal to 1. Actually, we saw already another indeterminate form, namely sine of x over x. Okay, we already I computed this limit already using the squeezing theorem. This is also an indeterminate form of type 0 over 0. Right. So if you use the rules of the L'Hopital, then you have to differentiate the sine, which is the cosine of x. You have to differentiate x, which is 1. Now, provided that this limit exists, they are equal. But this limit exists, and this is equal to 1. Okay, that's what we computed before. This is an interesting example. I just want to say a few words about this example, because if you think about it carefully, then what we are doing here is actually we are not allowed to do this. Because why do we know that the derivative of the sine is the cosine? I proved it, right? And for the proof, I used that this limit is equal to 1. So in order to know that the derivative of the sine is the cosine, you need to know that this limit is equal to 1. So you cannot use the fact that the derivative of the sine is the cosine in order to evaluate this limit. You understand? Because otherwise you use something which you need in order to understand that the derivative of the sine is the cosine. We call this in mathematics cycling. Sometimes this happens. So sometimes you are going to use something already of what you want to prove in order to prove it. Can sometimes happen in complex proofs, and sometimes easy to oversee. So for this example, strictly speaking, you are not allowed to use the rules of the L'Hopital to compute the limit. The same actually is true for this here, because I used here that the derivative of the ln is 1 over x. But if I know this, then I know already that this limit is equal to 1, because that's the derivative of ln of x at x is equal to 1. Okay, so these are not terribly interesting examples. So maybe some other examples. Sometimes one has to use the rules of the L'Hopital several times. So this is an indeterminate form of type infinity over infinity. So using the rules of the L'Hopital, you have to differentiate the numerator, which is e to the x, and the denominator, which is 2x. But actually there is a question mark, because I have to check whether this limit exists or not. So far I don't know this, because this is again indeterminate form of type infinity over infinity. So I can again try to use the rules of the L'Hopital. So I have here e to the x and here 2. Now I can compute it. Now it's infinity. Actually there is also a question mark here, but once I know that this limit is infinity, okay, then all the assumptions are satisfied. So now indeed those two limits are the same. And because this is also now equal to infinity, also those two limits are the same. Okay, another example. A one-sided limit. So the limit x tends to pi from the left sine of x over 1 minus cosine of x. This example is to demonstrate that it's very important that you check the assumptions. If this is not the indeterminate form, those two limits are not necessarily the same. This is an example because this is not the indeterminate form. Because the limit of the numerator is 0, the limit of the denominator is 2. So it's actually not 0 over 0. And indeed, if you take derivatives, then the limits are not the same. Cosine over x divided by sine of x. So now you see, this is minus infinity. Because in the denominator you get 0, but the denominator is always positive, and in the numerator you get minus 1. So it's minus infinity. But this limit is not equal to minus infinity. So you see, it's important to check whether you really have an indeterminate form or not. A final interesting example is the following one: x squared plus sine of x divided by x squared. So this is infinity over infinity. So it's an indeterminate form. So let's try to use the rules of the L'Hopital. So we get here 2x plus cosine of x divided by 2x. This is again infinity over infinity. So we do the same once more. So this is 2 minus sine of x divided by 2. Now actually, as I mentioned before, actually you have here question marks. Because we haven't checked yet whether this assumption is satisfied. Why is now this echo? Do anything. I'm not sure how to. Maybe now it's better. Yeah, now it's better. So actually you have these question marks here because I haven't checked this final assumption yet, right? But you see now this limit here. This limit doesn't exist, but it's not infinity. It's also not minus infinity. So this means I don't have equality between here and here, and also no equality between here and here then. So for this example, I'm not allowed to use the rules of the L'Hopital. So I need something else in order to compute the limit. But what is the limit? Who can tell me what is the limit? So it doesn't work. This doesn't work here. I can erase it. So sometimes it can be really the case that you use the rules of the L'Hopital several times, and then you discover, okay, this assumption is not satisfied, and you are not allowed to use them in the first place. Any idea what is this limit? You just have to write this function as 1 plus sine of x divided by x squared. And then sine of x divided by x squared is larger or equal than minus 1 over x squared, and smaller or equal than 1 over x squared, because the sine of x is bounded between minus 1 and 1. Now as x tends to infinity, this goes to 0 and this goes to 0 as well. So this tends to 0. So you see the limit is equal to 1. Okay, so you have seen some examples. This is a quite powerful way of computing limits. There are actually a couple of more indeterminate forms, namely also indeterminate products, indeterminate differences, and indeterminate powers, for which you can also use the rules of the L'Hopital by first suitably modifying the given limit. So let's first discuss indeterminate products. So this is a limit of a product f of x times g of x. X tends to infinity. Not necessarily to infinity. X tends to a. Where the limit of f of x as x tends to a is equal to 0, and the limit of g of x as x tends to a is equal to plus minus infinity. So here we say an indeterminate form of the type 0 times infinity. Now you can use here also the rules of the L'Hopital, because you can just write the product as a quotient. For instance, in the form f of x over 1 over g of x, or g of x over 1 over f of x. Now, if you write it like this, you get 0 over 0. And if you write it like this, you get infinity over infinity. And then you can just use the result I showed you before. So indeed, this is an indeterminate form, because you can reduce it to something which is 0 over 0, infinity over infinity. And we saw for a limit of this form, you can have the limit exists, or maybe it doesn't exist. And it can be any value actually if it exists. So a simple example is the limit x tends to 0 from the right of x times ln of x. So you can either decide to bring it in this form or this form. It's probably better to have the ln of x in the denominator and then 1 over x. Just because if you do it the other way around, then you have to differentiate 1 over ln of x, which gives a more complicated function. And then by using the rules of the L'Hopital, so the derivative of ln of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. So this is the limit x tends to 0 from the right, then minus x, and this is just 0. Okay, so that's one example. Another example is, for instance, the limit x tends to infinity, x times a to the 1 over x minus 1. You see, this is also of type 0 times infinity. So here, for instance, you can you can write this in the form a to the 1 over x minus 1 divided over 1 over x. And then again by, so now it's 0 over 0. And now again by using the L'Hopital, so if you wanna differentiate this, you have a to the 1 over x times ln of a times the inner derivative, which is minus 1 over x squared, and the derivative of the denominator is also minus 1 over x squared. So you can cancel this one. And then you can compute the limit. As x tends to infinity, what you get here is a to the 0, which is 1. So the result is ln of a. There's actually, for this example, there's another way to see this, because here you could do a change of variable. As x tends 1 over x goes to 0. So you could also look at the limits. U tends to 0 from the right, because this is always positive, and then a to the u minus 1 over u. But that's just the derivative of a to the u at u is equal to 0, and that's indeed ln of a. So you can also sometimes you can also use derivatives in order to compute limits. You don't need to use the L'Hopital. So these are indeterminate. The next thing are indeterminate differences. So indeterminate difference is the following situation. You have the limit of f of x minus g of x as x tends to a, with the limit of f of x as x tends to a equal to plus minus infinity, and the limit of g of x as x tends to a also plus minus infinity. It's maybe important to point out here that either both of them tend to infinity or both of them tend to minus infinity. If the limit of f of x tends to infinity and the limit of g of x tends to minus infinity, then it's not an indeterminate form, because then you have infinity plus infinity, which is infinity. Only infinity minus infinity is not clear. So this is an indeterminate form of the type infinity minus infinity. Okay. So either both of them are plus or both of them are minus. Not, for instance, this one is plus and this one is minus, or this one is minus and this one is plus, also not allowed. In these cases, you don't have an indeterminate form. And for these situations, it's actually, there is no clear rule how to solve the limit, but depending on the function, you can usually use common denominators, or first some simplification in order to transform it into a form 0 over 0 or infinity over infinity, and then you can use the rules of the L'Hopital. For instance, the example in the textbook is the limit x tends to pi half from the left, the secant of x minus the tangent of x. This is an indeterminate form because the secant is 1 over the cosine. The cosine at pi half is 0, so this the limit of the secant of x as x tends to pi half from the left is infinity, and for the tangent the same. So you have here infinity minus infinity. Now the way to compute this is to write out the definition of the secant and of the tangent, and then to write only one fraction. So you have cosine of x in the denominator and 1 minus sine of x in the numerator. So this is now indeed 0 over 0. So this is the same as the limit x tends to pi half. Derivative of the numerator is minus the cosine of x, and the derivative of the denominator is minus the sine of x. And now you can compute it. So the cosine at pi half is 0, and the sine of pi half is 1, so it's 0. So this limit exists, so indeed this limit is equal to this one. And the last situation are quotients. Here we want to compute the following limit. So the limit of f of x to the g of x. This also sometimes gives you an indeterminate form, because you can write this using the exponential function as e to the g of x times ln of f of x. Now in the exponent you have a product. So the product could be 0 times infinity. There are 3 situations where this can happen. If the limit of f of x as x tends to a is equal to 1, and the limit of g of x as x tends to a is equal to plus minus infinity, then you have in the denominator 0 times infinity. Another case is if the limit of f of x as x tends to a is equal to infinity, because then the ln is also infinity, and the limit of g of x as x tends to a is equal to 0. And the third situation is the limit of f of x as x tends to a is 0, because then the ln becomes minus infinity, and the limit of g of x as x tends to a is also equal to 0. So these are all indeterminate forms. In the third case you have 0 to the 0. In the second case you have infinity to the 0. And in the first case you have 1 to the plus minus infinity. The first one is maybe the one most often overlooked, because you might think 1 to the plus infinity should be 1. Okay, but actually this is an indeterminate form. If this limit here is 1 and this limit is infinity, then the whole limit is not equal to 1. Okay, because if you write it in this form, then in the exponent you have a 0 times infinity, which is an indeterminate form. So that's quite often overlooked, because you might think 1 to the infinity should be 1. And the way to handle these situations is just to write it in this form, and then you have 0 times infinity in the exponent, and then you use what we discussed for 0 times infinity. So for instance, For instance, if you want to compute the limit x tends to 0 from the right of x to the x squared, for instance, this limit. Okay, so this is an indeterminate form because it's 0 to the 0. It's this case. So you write it as the limit x tends to 0 and then e to the x squared times ln of x. Now, because e is a continuous function, it just boils down to computing this limit. You can take the limit into the exponent. So you have to compute this limit. Now this limit this is also indeterminate form, 0 times infinity. So you write it as the limit x tends to 0 and then ln of x divided by 1 over x squared. Now it becomes infinity divided by infinity. So now you can use the rules of the L'Hopital. So this is the limit x tends to 0 from the right. And then you have here 1 over x in the denominator. And in the numerator you have minus 2 over x to the cube. So this is equal to, you can take out minus 1/2. And then you have the limit x tends to 0 from the right. And then it's x squared. So this is just equal to 0. So the limit in the exponent is equal to 0, so this limit is equal to 1. Okay, maybe one final example. One final example. So the limit of 1 plus 3 over x plus 5 over x squared to the power of x, x tends to infinity, not 0. This is also indeterminate form because this function here tends to 1. X tends to infinity, so you have 1 to the infinity. So that's this type here. That's the case what I mean. It is not equal to 1. Okay. Now, just using the same trick, so you have the limit x tends to infinity, then e to the x times ln of 1 plus 3 over x plus 5 over x squared. And again, you can write the limit in the exponent, so the limit x tends to infinity, x times ln of 1 plus 3 over x plus 5 over x squared. So what I have here now is infinity times 0. So in order to handle this, the limit x tends to infinity of x times ln of 1 plus 3 over x plus 5 over x squared. We write it again as a fraction. So the ln of 1 plus 3 over x plus 5 over x squared divided by 1 over x. So now it's 0 over 0. So this is equal to the limit x tends to infinity. Now the derivative of this one is 1 over, by the chain rule, 1 plus 3 over x plus 5 over x squared multiplied with the inner derivative, which is this one is 0, this one is minus 3 over x squared, and this one becomes minus 10 over x to the cube divided by 1 over x squared minus 1 over x squared. That's the derivative of the denominator. Now we are actually almost done, because this limit, if I just look at this limit is 1. And for the rest, if I multiply with x squared, I see that it's 3. So this is 3. So this is e to the 3. That's this limit. Right, because the limit of this one is 1. And the limit of this one, I multiply everything with x squared. Then I have here 3 plus 10 over x, which as x tends to infinity is equal to 3. So it's 3. The limit is 3. Okay. So you see the rules of the L'Hopital. Strange. Now the echo is suddenly gone again. I don't understand this. So you see the rules of the L'Hopital. They're quite useful. Quite easy to apply also. So the only thing you need to know is how to differentiate functions. This gives you this allows you to compute the limits of quite complicated expressions. So this kind of in addition with the together with the limit laws, we can now compute almost all kinds of limits which we want to compute. I maybe should stress that even the derivative of the definition of the derivative is also an indeterminate form. Okay, because the derivative of a function at the point A was defined as the limit x tends to A, f of x minus f of A divided by x minus A. So that's also an indeterminate form. Okay, that was the definition of the derivative. But of course you cannot use here the rules of the L'Hopital, because you want to figure out what the derivative is, and you cannot use the rules of the L'Hopital require you to know already what the derivative is. So actually, when we started to talk about derivatives, we already started to talk about indeterminate forms. Okay, but we found other ways of evaluating those indeterminate forms. Okay, the rules of the L'Hopital are just really useful for now more complicated functions. Okay, which are not just derivatives. Okay, so this concludes the section. This should have been 4.4 in our textbook. The next section we have optimization problems. I don't know which number in the textbook it is. And in this section we want to come back to the problem of finding maximum and minimum value. Usually absolute maximum and absolute minimum value. So so-called optimization problems ask for the optimal solution of some problem, which usually requires you to find the maximum or minimum. For instance, an example is I mentioned this example at the very beginning of chapter 4. If you are producing cans out of tin, you usually know how the quantity which should be filled into one can. For instance, every can should hold 1 liter. Okay, and under this assumption, if the can is cylindrical can, how to choose the dimensions of the cylindrical can such that the volume gets maximal. This is something which might interest you if you produce cans. No, I said it wrong, because you know that the volume is already 1 liter. So what you want to do is you want to minimize surface area. Okay, because if you can minimize surface area, then you don't need to use so much tin for producing one single can. So you can you can reduce your production. So this is an example of an optimization problem. So usually you have you have such a problem. You have given a certain function, which usually depends not only on one variable but more than one variables. But you have also some constraints, and using the constraints, you can eliminate all of the variables except one. And once you have a function of only one variable, you can use what we discussed so far in order to find absolute maximum and absolute minimum, or local maximum and local minimum, depending on what is required. So these are so-called optimization problems. I'm not sure whether I should I still have 8 minutes. Okay, so let's maybe start with one of them. So the optimization problem I just mentioned was how to choose the dimensions of a cylindrical cell of a cylindrical can holding 1 liter of I don't know, oil, such that the surface area gets minimized. So usually optimization problems are in text form. Now the first thing you should do is, after reading carefully what the problem asks you to do, usually to plot a picture. So the cylindrical can looks like this. The next step is usually to introduce notation. So let's say this is h, and let's say the radius of the base of the can is equal to r. Now what you have given is the volume. The volume is r squared times pi times h. You know this is equal to 1 liter, which is 1000 cubic centimeter. So that's what you have given. And what you want to optimize, what you want to minimize is the surface area. So the surface area is twice the area of the circle with radius r, which is for the bottom and for the top, plus, and then you have what is called the lateral surface area, which is just, if you just slice it open, flatten it out, it's just a rectangle whose side lengths are h, the height, and the other one is the circumference of the circle, which is 2 times r times pi. So plus h times 2 times r times pi. Now, this is a function of 2 variables, because apart from r you have also h, but you have also a constraint. So you can solve here, for instance, for h. So h is equal to 1000 divided by r squared times pi. And then you get a function of just one variable. So a is equal to 2r squared pi plus, and then 2000 over r pi over r. Okay, so that's the function which you have to optimize. And you also have a range of r, so r is just anything larger than 0. And since this is now a function of just one variable, namely r, you can just use what we learned before. So the derivative with respect to r is 4 times r times pi minus 2000 divided by r squared. And this you have to equate to 0. So what you get is r to the cube is equal to 2000 divided by 4 pi. So it's actually 500 over pi. So this is 500 over pi. So r is equal to the third root of 500 over pi. Now I wanted to have a minimum. So why is this the minimum? Because this is just a critical point. Okay. But you see here that you see that the first derivative is smaller than 0. Interval from 0 to this solution here, let's call it star. And it's larger than 0. On the interval from r star to infinity. So you see that the function, this function, if r is smaller than r star, is always decreasing. If r is larger than r star, is always increasing. So of course this must be not only a local minimum but also absolute minimum. So that's usually actually I didn't finish because what I'm asking for are the dimensions. So actually you have to plug it in here and to compute the h. If you plug it in, you will see this equal to the corresponding h value is equal to 2 times r. I shouldn't write it here. So the corresponding h value is 2 times r star. If you do the computation, you see this easily. So I asked for the dimensions, so I asked for h and r, where the minimum occurs. This is the r you have to choose. This is the h which you have to choose in order to have the minimum. So this is how these optimization problems usually. You have to carefully read it. Then usually you should make a picture. You should introduce notation for the quantities which are involved in your function. Then your function which you have to optimize usually is a function which depends on more than one variable. Here 2 variables, r and h. But you have also constraints. The constraints will help you to eliminate all the variables except one. Then you have a function of only one variable. And then for this function you can just use the tools which we have discussed before in order to find usually absolute maximum and absolute minimum. So you also have sometimes, not in this example, sometimes the function you have is on a closed interval. Then you just use the closed interval method. But sometimes the function, the domain is not a closed interval. Okay. Then you it's not enough just to look at how the derivative behaves to the left and right of the zeros, because this just gives you local extrema. But if you are interested in absolutes, you need something more. Like if you have a function and on some domain, and you have only one critical point, and the function is always decreasing to the left of the critical point and always increasing to the right of the critical point, then you have not only a local minimum but also absolute minimum, like in this case. So there is, in the textbook, you have a first derivative test for absolute extrema, which I just have formulated. So next time I'm going to formulate it. Next time I'm also going to discuss some more optimization problems. And then we are almost finished with the theory of differentiation. In the second half of the course, we will discuss integration. Don't forget, next week, there is no class next week, there's only the midterm. So from 9:10 to 11. So I will continue in 2 weeks. Any questions?